All right, this is note card number 3, analytical strategies for finding limits. So now we're looking at limits, but we don't have a graph. And graphs are probably the easiest way to see limits, but we're going to have to be able to find these limits even when we just have equations. So these are kind of the how you find limits. The first thing you want to try is direct substitution. So just plug so in this example, for instance, we're just going to try to plug pi in for theta, and if we get a value, then we're done. That's the limit. But sometimes we're not going to be able to get a value. And a good example of that is if we try to plug 1 in, you guys can see that if we plug 1 in for x, 1 minus 1 is 0, and we're going to have it divide by 0. So that's a problem. So the second technique that we're going to try is factor and cancellation technique. And we'll talk a little bit more about why that works. And then the last kind of limit is a special trig limit. So typically we're going to be dealing with sine, and as x approaches 0, the sine of x and x become really similar, and so the sine of x is basically x, and then that's divided by x, and x over x is 1, so that's why we see 1 here, and we'll talk a little bit more about why that works as well. Let's run through some examples. So first, as I said, we're going to try direct substitution on this first one. That's just going to give us pi secant of pi. Now secant of pi is the reciprocal of cosine of pi, and cosine of pi is -1. The reciprocal of -1 is still -1, so we have pi times -1, which equals -pi. So that's the answer to the first one. And notice, sometimes with these limit questions, it's not going to be the concept of limits that holds you up. It's going to be your trigonometry and algebra skills. So make sure you are still practicing that trig stuff and those algebra skills. Number 2, as we said, if we try to plug 1 in, we're going to get a divide by 0. So that's a problem. So what we can try to do if we run into that situation is factor the top. And so we're going to get x plus 6 and x minus 1 over x minus 1. And what you notice is we can cancel those x minus 1s. And so we're just left with x plus 6. And if we plug, so essentially what's happening is this function right here looks exactly the same as x plus 6. It's just that there's a hole at +1. So if we wanted to look at the graph of this, we might see something like this, and in x squared plus 5x minus 6 over x minus 1, there would be a hole at x equals 1. And so as we approach from the left and as we approach from the right, we're going to be approaching this value right here. So kind of the trick here is that we're by canceling the x minus 1s, we're getting rid of the hole, and then we can just inspect whatever that value is. And so we're left with x plus 6, and then we can just plug the 1 in for that, and we get 1 plus 6 equals 7. So the answer to that one is 7. And this is a pretty common kind of limit that you'll have to find. All right, number 3, as x approaches pi over 6, we can just evaluate this one. The cosine of pi over 6 is, and remember the unit circle, pi over 6 is right here, so the cosine of that is going to be root 3 over 2, positive root 3 over 2. All right, number 4. This one's a little trickier. What's different about this one is we're not approaching a number value, we're just approaching the value a. And this is a little bit more abstract to approach the value a, but if we tried to plug in, if we just go through, okay, let's try direct substitution first. We get a minus a over a to the fourth minus a to the fourth, and that gives us 0 over 0, so that doesn't seem to work, right? That's an undefined value, so we're not finding the limit in that case. So what we need to try next is try factor and cancel. And I know this looks a little tricky to factor, but x minus a over x to the fourth minus a to the fourth is a difference of squares, so that's x squared plus a squared times x squared minus a squared. And then that factors even more. X squared minus a squared is also a difference of squares, so I can simplify, or I can expand that out even more to x plus a times x minus a. And now what we notice is we've got an x minus a on the top, x minus a on the bottom, and at this point we can plug a in for x. And so if we go ahead and plug a in for x, we get a squared plus a squared times a plus a in the denominator, and then since we canceled these, those go away. We're left with, don't forget, we're left with 1 on the top, and a squared plus a squared, that's 2a squared times 2a, which then simplifies to 4a cubed. And so our answer to this one is 1 over 4a cubed. Moving on to number 5, find the limit as x approaches negative 4 of r of x if r of x, and now we see a piecewise function. So I want you to visualize the graph of this. Remember, limits are so much easier to see or understand when we're thinking about the graphs. What we have here is a quadratic that dictates the function 2x squared minus 3, and so probably looks something like this. And we're told that for everywhere that's not negative 4, that quadratic is dominating, and then at negative 4, we're not going to look at the quadratic. We're going to look at the point 1.7. So we probably have something that looks like this, where here's 1.7. So for any value that's not negative 4, we will use the quadratic, and then at the value negative 4, there's sort of this random point that looks like it's below the quadratic. Now a limit doesn't care whether the point is there or not. We're just saying as we approach negative 4 from the left, and as we approach negative 4 from the right, what value are we approaching there? It's not about what the value is of the function. It's what are we approaching from the left and what are we approaching from the right. So in order to figure out this value, we just need to know what the value on the quadratic would be. So what I'm going to do is I'm going to plug negative 4 into the quadratic function. So that's 2 times negative 4 squared minus 3. And negative 4 squared is 16. So we have 2 times 16 minus 3. 2 times 16 is 32. So we get 32 minus 3 equals 29. So the limit as we approach negative 4 of r of x is 29, even though the value of the function at that point is 1.7. The limit is 29. Great. Number 6, the sine of 5x over 2x. This is a really easy one because as we approach 0, the sine of 5x becomes basically the same as 5x. And 5x, we have 2x on the bottom, 5x on the top. The x's cancel out, and we're left with 5 over 2. So that's how you do a special trig limit like this. And you can kind of see that definition up here. That's called a special trig limit. The reason this works goes to the unit circle. So essentially, if we have an angle here, let's say pi over 3, and the angle really measures the distance around the circle, on the perimeter of the circle, whereas the sine of that angle is just the vertical distance. And so you can see that the angle itself, which is this perimeter, is a bigger value than the vertical piece here. So the perimeter of the circle is more than the sine of the angle. So the angle is greater than the sine of the angle. But as we take that angle and move it down the circle and approach 0, what happens is the sine of the angle, so the sine of the angle and the angle itself become almost identical as we get really far down towards 0 on this unit circle. And so sine of 5x and 5x become the same for all intents and purposes as we go toward the limit. And so the sine of 5x we can say is just 5x, and then we have 2x on bottom. We cross out the x's, and that's why we're left with 5/2. Alright, number 7, it says if g of x equals 3x squared minus 5, then the limit as x approaches 0 of g of x minus g of 0 over x cubed equals what? And this is an actual AP question. Why don't you go ahead and try it before, so pause the video, try it, and then come back for the explanation. Alright, so the trick here is basically we're going to substitute 3x cubed minus 5n for g of x. And then g of 0 is when we plug 0 in, and that just equals negative 5. So I'm going to subtract negative 5, that's what g of 0 ends up being, and then that's over x cubed. So because we're subtracting a negative here, we're really adding 5. So this is the same as plus 5. Negative 5 plus 5, those go away, and we are just left with 3x cubed over x cubed. We can cancel the x cubes, and we are left with 3 over 1, which is 3. So the answer to number 7 is the limit is 3. And that is how you evaluate all these different kinds of, or find all these different limits. You always want to try to use substitution first. If that doesn't work, try factoring and canceling. And if it looks like it's a sine of x over x as x approaches 0, and that's really important, it's when x is approaching 0 that this works. You can simplify that to, in this case, 1, or if you have something like this, you basically get rid of the sine and cancel out the x's to be left with 5/2. So that's note card 3. Hope limits are starting to make more sense.